In section 2, we're going to look at some additional constructions inside of a circle. So we can move the vertex, we can have lines come up, tangent lines come up to a circle, and different things start to happen. So the first one we're going to talk about is an inscribed angle. In this example here in the red, angle ABC is an inscribed angle. And an inscribed angle has the vertex on the circle. So remember, a central angle had the vertex at the center. An inscribed angle has the vertex on. What happens is if this angle measure is x degrees, the arc is 2 times the angle. So central angles were equal. Inscribed have a relationship of a factor of 2. So one way to think about it is if you know the angle, then you multiply for 2 to get the arc to equal the arc. And if you know the arc, you divide by 2 to get the angle. Right? So it's a matter of going out, you multiply by 2. When you come in, you divide by 2. So when we look at this picture, for our example, it initially looks very complicated, but if you just begin to trace your angles and your arcs, so here's an angle I want to know, and it comes out and it cuts this arc, which is 100 degrees, and when I go in, I cut it in half, and so x is 50. If I move around to this arc and its corresponding angle, when I move from the angle out to the arc, I multiply by 2. So y is 68 degrees. Now initially it might seem that I don't have enough information to find z. But remember, all the way around a circle is 360 degrees. And so, if I wanted to know this arc right here, I would take 360 should be equal to, I'm going to call this A plus 76 plus 68 plus 100 plus 62. All of the arcs added up have to equal 360. So when I work that all out and subtract, that arc is 54. And once I know that this arc is 54, when I move in to find its angle, I have to cut it in half, and this becomes 27. So it's just a factor of 2 in or out. Trace your angle out to your arc. In this scenario, my my inscribed angle is right here, and it's going to cut this arc. Well, indirectly, I know this one is 254, so the green one has to be 360 minus 254. So that means the red one is 106. And when I move into my angle that is inscribed, that is vertex on the circle, I cut it in half, and that makes it a 53 degree angle. Now this next theorem should seem familiar because it is very much like the perpendicular bisector theorem that we had in lines and triangles. If you remember, one of the things that was also true in the perpendicular bisector theorem was that these guide wires, OA and OB, were equal, and in fact those are both the radius of that circle, so they are equal. So we see that holding true. So everything else that's true in here, that this gets bisected and there is a right angle, is basically from that perpendicular bisector theorem. The most important thing to note here, though, is what is and what is not bisected. So AB is bisected. That chord that cuts randomly across the circle. It's not a diameter, it's not a radius, it's kind of a random chord cutting across. But this radius of OC is not bisected. And that is super important. OC is not bisected. That is the radius. So you have to remember, it's kind of like in a kite, which part is bisected and which part is not bisected. So if we look at an example, as always, let's just look at our picture to start with. QP is my perpendicular bisector. So that is 10. That makes this 10. I can always draw in radius if I want, and if that helps me work my picture. And often we're going to do that because it makes right triangles. Additionally, I'm given the information that this arc is 150 degrees. And so if that arc is 150 degrees, WQR is the central angle, so that angle is 150 degrees. And if you remember from the perpendicular bisector theorem, these angles get bisected, so each of those angles is 75. So when it asks for arc WP, here to here, that traces back to that 75 degree angle, and so we know that central angle is 75 degrees. When it asks for WR, WR is the length of this whole chord. That part was 10, it's bisected, this part is 10, so the whole thing is 20. The picture's kind of a little messy here. So then when I go to look at the last question, it says QX is 5. How big is QP? Now QP is a radius, but as it stands, I'm not going to find QP directly. I can find any radius, and in fact the radius that I am going to use that's most interesting is the one that is part of this right triangle. And so if you drew it out separately to see it, you would have W, this is 10, this is 5, X, and Q, and my radius, QW, which is also the same as QP because that is a radius of the circle, just the same as if I drew a radius out here, all of those are the same length. So this is now a Pythagorean theorem. The radius is the hypotenuse, and so R squared is equal to 5 squared plus 10 squared. And so when we work that out, we end up with R squared is equal to 25 plus 100. R squared is 125. R is equal to the square root of 125, which is approximately 11.2 units.